Hello students, welcome back to this lecture on the delay of NAND and NOR gates. In this particular section, we will look into more about P plus GH model. We have seen an Elmore delay method and utilize that particular model or the Elmore delay method to estimate the delay. Maybe it is a falling delay or a rising delay. This particular model, let me use my pointer. So this particular model is also called as P plus GH model, and it is a linear delay model. So it doesn't involve any long. So the delay, whatever we estimate, it will not be a non-linear function of the of the capacitance or the scaling. Right. So it is a very linear model. And the overall delay, when I write the small lowercase d, it means that it is a normalized delay. So it means that it is, the absolute delay has been taken for a particular gate and then it has been divided by the inverter's delay. P plus GH, as we had seen in the last lecture, and then this P represents that this is a parasitic delay. And then this GH can also be considered as an F value, which is nothing but the effort delay, where F is nothing but G into H. The G is called as a logical effort and H is called the fan out of the electrical effort. Right. So this particular definition of the fan out we had seen earlier, it is nothing but the input capacitance, or rather we had seen the load capacitance divided by the input capacitances. Right, what it means is it's nothing but the H value is nothing but whatever is the input capacitances given by the next stage. So that is our load capacitance, and it's divided by the first stage, or whatever the stage we are considering at this point of time, its own input capacitance. Right, so that is the fan out of the electrical effort. Logical effort, and then we will see a little bit later, and then the parasitic, which is a normalized parasitic, also the definition of it and then the expression for it we'll also see in the future slides. So if I'm considering that inverter, for this particular linear delay model, if I want to estimate the delay of the inverter is nothing but inverter driving H inverters. So I have one inverter in the first stage driving another inverter and H such inverter in the second stage. So this is what the stage or the H represents here. So I'll get a 3 RC. So I'm assuming this is 2:1 ratio. This particular inverter is also 2:1 ratio. This is also 2:1 ratio, and then this is also 2:1 ratio. Right, so I'll get each of this delay will give me the output node capacitance is 3C here, switching resistance is R, so I'll get 3 RC, and then plus the input capacitances here coming from here is 3C, and then so on, 3C into H multiplied by R, and then because it's a normalized delay, so I'll actually divide it by 3 RC. So finally I will get 1 plus G into H, so P plus GH, where P is nothing but 1, G is nothing but 1, and H is nothing but the value of H. Right? How many number of inverters I am using it in the second stage, or I'm designing it in the second stage. So this is nothing but P is nothing but 1 here, G is nothing but 1 here, and H is whatever is the number of inverters that we have designed for the second stage. Okay, hope you have understood this particular linear delay model. Right, I have an empty slide. That means that I have to draw something here. So let's go back to our 3-input NAND gate, and I'm going to draw the 3-input NAND gate circuit again. So let me use a different color. So this is my PMOS side, and PMOS, the input should be bubbled here, and this is my output, and then on the NMOS side I will have the 3 transistors in series. Right, so these are the inputs A, B, C. What we had seen up till now is, especially for using the Elmore delay method, we had used this internode diffusion capacitance of 3C. So assuming that the sizes are 2, 2 and 2 here and then 3 here, we get the capacitances here, the diffusion capacitances of 3Cs. Right, and then finally the output node capacitance is 2 plus 2 plus 2 plus 3 will be nothing but the 9C capacitance. So this is ground. Right, so this is what we had used, and then using the switching resistance for each of these transistors, we got the propagation delay falling to be nothing but 12 RC. And here I'm going to write it as the Elmore delay method. Right, the linear delay method, it sees only one capacitance, right? So it sees the output node, and it considers only the output node capacitance. So the capacitances which are associated at the output node, and it doesn't consider any of these capacitances, the internode diffusion capacitances. So whatever is the capacitances at the output node, it takes that into account, the linear delay model, and then the propagation delay falling using the linear delay model is nothing but 9C into whatever is the switching resistance and then the path that the switching resistance makes with respect to the sources, right? So in this case, it is the source is the ground. In the rising one, the source will be nothing but VDD, right? So in that case, the equivalent switching resistance or the discharging path switching resistance will be R by 3 here, R by 3 here, R by 3 here. So it will be nothing but R. So finally, my value is nothing but 9 RC. So the linear delay model doesn't account for the internode diffusion capacitances, which was 3C and 3C, in which we had used that to find out the propagation delay falling using for the Elmore delay method. But the linear delay model doesn't consider that, and it considers only the capacitances that is connected at the output node. Right, so that is a major difference. So the linear delay model is a much more approximation than that of the Elmore delay method, but it is kind of very handy, and then in the sense it's a very fast method to arrive at the delay parameters. So given a circuit or given a schematic, I should be able to see only the capacitance at the output node and then multiply by whatever the switching resistance that gets connected to the ground or gets connected to the VDD, and that will be my the overall delay. The other advantage of this linear delay method was if you consider the propagation delay falling, I get 9C into R, right? And if I consider the propagation delay rising using this linear delay model, right, it will be nothing but this particular capacitance 9C multiplied by R on the other side. So if I consider this as a VDD, the switching resistance in the worst case condition is still R, considering one of the transistors will be on. So the rising delay using the linear delay model is also 9 RC. So effectively, the propagation delay rising and falling in the linear delay model, if we consider the gates to be having the equal rising resistance, the falling resistance to that of the 2:1 unit inverter, we should get both the propagation delays same. All right. Whereas in the Elmore delay method, when we had applied and calculated or estimated the delay, it was different. So the rising delay was 15 RC, the falling delay was 12 RC. Right. So that is a major, major change or difference between the Elmore delay method and then the linear delay model. Although the Elmore delay method is much more accurate, the linear delay model is just a model just for a faster estimation of the delay, right? Hope you have understood this. Moving forward, so if I use the linear delay model for a 3-input NAND gate, so I will have this 9 RC, which we had estimated from the previous slide. And if I have, the second stage, I have H number of 3-input NAND gates, I will get 5 HC and then multiplied by the switching resistance for the pull down or the pull up will be nothing but R. So this 9C is coming from the capacitance seen at the output node only, and not any of the capacitance from the intermediate node diffusion capacitances, right? So I will consider this 9C coming from only the output node capacitance. And then this phi h is coming from the other stage input capacitance multiplied by this R. And because it's a normalized value, so it is always divided by 3RC of that this is coming from the inverter. So this is nothing but the inverter delay. So overall, I'll get 9 divided by 3, which is nothing but 3, and then phi h by 3. So where 3 is nothing but the parasitic value, the normalized parasitic value. Phi by 3 into h, so we will take this G as phi by 3 and h as the fan out or the electrical effort. Right? Turns out that the fan out is nothing but the load capacitance divided by the input capacitance of the first stage. So the load capacitance is nothing but h times phi c, and then divided by the phi c its own input capacitance. So this phi c and phi c gets cancelled. So this fan out is nothing but h, which reiterates that h is not the number of gates. It is, or it is not the number of wires that is going to the next stage. It is basically how much of the load capacitance is the ratio of the load capacitance with respect to that of the its own input capacitance, right? G is the logical effort and P is the normalized parasitic factor, which is 3 and 5 by 3 respectively. So this, once again, I have explained the H is nothing but the C load capacitance divided by the C input capacitance of its own stage. Logical effort is the input capacitance of the gate divided by the input capacitance of the inverter. So it is basically, this 5 by 3 is basically the benchmarking of the, it's basically a ratio of the gate input capacitance and that of the inverter's input capacitance. So we are basically checking the driving strength of the gate with respect to that of the inverter, right? Although I have put here, the ratio should be accommodated in such a way that we should get the same output current, right? So what it means is, if I'm taking the 2:3 NAND gate, right? 2:3 3 input NAND gate, I'm having the capacitance, the output node capacitance actually discharging at a current of I. Whereas with respect to the inverter of 2:1, I will have the same, this particular 2:1 inverter is also going to discharge with the same current of I. Because in both the cases, we have adjusted the sizes on the NMOS and PMOS so that we will get this, the resistance, the falling and the rising resistance of R for the 3 input NAND gate as well as for the inverter. So the capacitor discharging current will be I, and if that is the I value, then it will have the same I for the 2:1 inverter. So while we are defining the logical effort should always be defined, right, for a gate by benchmarking the inverter size so that both of them gives the same output current. Okay, and then I think this is something we will, the logical effort, we will take a deeper look into it in the future slides, in the future lectures. Hope at this point of time you have understood what is P, what is D, and what is H. Moving ahead. So we had seen for a 3 input NAND gate. So what should be it for a 3 input NOR gate? So for a 3 input NOR gate, again, we will adjust the sizes. We will design the sizes of the transistors such that we will get the rising resistance of R and then the worst case falling resistance to be R. So for a 3 input NOR gate, we will have on the pull down side all the 3 transistors to be in parallel. On the pull up side, we will have all the 3 transistors to be in series. Right, so if I have each of these transistors giving me R by 3 somehow, right, R by 3 and R by 3, then we will have the rising resistance to be R, which will match with that of the 2:1 inverter's rising resistance. So for that reason, we will have the size to be 6 for a PMOS transistors. And on the worst case condition, one of the transistors on the pull down side, if it is on, I will get the falling resistance to be R. So that means I will have the sizes to be nothing but 1, 1, and 1. So once we have identified the sizes, what should be we are going to the linear delay model. So I need to establish what should be the capacitance seen at the output node. So the capacitance is coming from this particular transistor, this particular drain to body capacitance is 1C. There will be a drain to body capacitance of 1C here, and then there will be a drain to body capacitance of 1C here, right? So the three capacitances will contribute to the output node. In addition to this particular, there will be a 6C capacitance from this PMOS transistor. So overall, I'll see a 9C capacitance. And if it is cascaded, if the output is going to the next stage, so the input capacitance for the A input, right, will be nothing but 1 plus 6, so it will be 7C. For the B, it will be 7C. For the C, it will be 7C. So the next stage, if it is connected as one of the inputs, to one of the A, B, or C, it will have a 7C. And if I have 7 such the NOR gates in the next stage, I will have 7HC. So the normalized delay for the 3-input NOR gate will be nothing but 9C plus 7HC into R, rising or falling, doesn't really matter. And then because it's a normalized value, I will have 3RC as the inverter's delay in the denominator side. So finally, I will get 3 plus 7 by 3H, right? Remember that for the 3-input NAND gate, we had a 3 plus 5 by 3H, okay? And then for the 3-input NOR gate, it is 3 plus 7 by 3H. Just to verify that same, if I go back to the previous slide, I will get this 3 plus 5 by 3 into H, right? So this particular value. And if I go back to the present slide, we can easily say that the NAND gate is much more faster because it is 3 plus 5 by 3. So this 5 by 3 will be a lower value than 7 by 3 value. So the NAND is actually much faster than that of the NOR gate, right? So in any kind of a design case, if we can accommodate the NAND gate instead of a NOR gate, one will go for the NAND gate because it is much faster. So the delay is actually less. Hope you have understood this. Moving ahead, so I've also drawn for 2-input NAND gates and then a 2-input NOR gates. So the sizes for a 2-input NAND gates will be on the PMOS side, it will be 2 and 2. So that will give me, in the worst case condition, it will give me a rising resistance of R. Right, on the pull down side, for a 3-input NAND gate, we had a size of 3, 3, and 3. So that will get R by 3, R by 3, and R by 3. Here it is only 2 transistors. So I need to have a switching resistance of R by 2 coming from one transistor and R by 2 coming from the another transistor. And hence, we should have a size of 2. So the overall capacitance seen at the output node Y will be nothing but 2 coming from here, 2 coming from here, and then 2 coming from here. So 6C. And if it is cascaded to the next stage, the next stage input will see a capacitance of 4C in both the inputs. So if it is connected to one of the inputs on the next stage for the same 2-input NAND gate, it will be nothing but 4C into H. So the overall delay, normalized delay in a linear delay model will be nothing but 6C plus 4HC divided by 3RC, which will be nothing but 2 plus 4 by 3 into H. Right? So it says that as the number of inputs, if I consider the 3-input NAND gate, it was 3 plus 5 by 3 into H, which is more than that of the 2-input NAND gates. Right? And the 2-input NAND gate is more than that of the inverter, which is nothing but 1, right? 1 plus H, 1 plus 1 into H. For a 2-input NOR gate, again, I've designed the 2-input NOR gate and made the sizes of 4 and 4 so that effectively I'll get the switching resistance as R by 2 plus R by 2 as R. And on the pull down side, if one of the transistors is on the NMOS side, I'll get the resistance of R here. So overall, at the output node, I will get the overall parasitic capacitance is nothing but 1 plus 1 plus 4, which will be nothing but 6C. And then plus, each of these inputs is going to see 4 plus 1, which will be nothing but 5C. So if this output gets connected to one of the inputs of the 2-input NOR gates, then I'll get 5C, and then H number of NOR gates in the second stage will give me 5HC. So overall, the normalized delay will be nothing but the same 6C plus 5HC into R divided by 3RC. And then finally, I'll get 2 plus 5 by 3 into H. So this is much lower than 3 plus 7 by 3 into H, which was for the 3 input NOR gate. But it is slightly more than that of the 2 input NAND gate. So again, 2 input NAND gates is better than the 2 input NOR gates. Similar to that of the 3 input NAND gates is better than the 3 input NOR gates because the delay is slightly less. Right? So at this point of time, what we had seen is the linear delay model for the inverter for the 2 input NAND gates, 2 input NOR gates, 3 input NAND gates, and then the 3 input NOR gates. So this is basically a graph of the normalized delay with respect to the number of H, right? The electrical effort or the fan out. So D versus H. If H is 0, right? So the electrical effort is 0. That means the effort delay is 0. That means the first stage is not putting any effort to the second stage, right? What it means is, if H is equal to 0, that means that the delay is only due to its own parasitic capacitances, right? Or the parasitic factor, right? So in that case, if I consider the inverter has the normalized delay, the linear delay model says, right, it is 1 plus 1 into H. So if H is equal to 0, right, it will be 1, which states that its own parasitic delay is actually 1, right? If I consider 2 input NAND gate, it is nothing but 2 plus 4 by 3 H. So that is, 2 input NAND gate is this one. It will start from 2 because when H is equal to 0, it is the 2. It is, this 2 value denotes that it is due to its own parasitic capacitance. There is a delay of 2, right? And then I will have this particular profile. Remember that the G value here, the G value here, the G value here, and of course the G value here, right, is nothing but the slope of this particular linear delay profile, right? The linear delay with respect to H, if I draw, the slope will be nothing but the logical effort. So this slope represents the logical effort. All right. And based on the H, I should be able to estimate what is the delay. So based on if H is equal to 3 or something, I should be able to find out what should be the inverter's delay, what should be the 2 input NAND gates delay, what should be the 2 input NOR gates delay, what should be the 3 input NOR gate, and then 3 input NAND gate, right? And if I consider the 2 input NOR gate here on this particular line here, so the slope is 5 by 3, and as the H increases, I'll get more and more delay. This particular linear delay profile also confirms that the delay parameter is nothing but with respect to H value, it is a linear function, right? And if I actually draw the Elmore delay model on this, you will see that it is a non-linear function. So that is the basic difference, right? So the linear delay model, if I draw the profile of delay with respect to the H value, we will see that it's a linear profile, right? It's a linear function with respect to H.